in an Excel file that I've named lesson underscore unit 3 underscore last name. In my case, I put SNAR. In your case, you put your last name. So you want to save this file. We're going to do this in worksheet L1. In this problem, experience leads you to believe the time that it takes for the next train to come, T, follows uniform distribution with probability distribution function of f of t equal 1 divided by 24. T ranges from a minimum of 7 to a maximum of 31. Now notice that 31 minus 7 is 24, right? Now the thing about this is this cannot be known. You'll never know what this is. So you're kind of like assuming that you're a god here. Only gods know the truth in statistics. So this is a theoretical distribution that we cannot know. Now, at the bottom of this problem, there are data for 64 randomly picked travel days. I'm going to copy it first to Excel, and then I'm going to copy it to this website. So let's grab that. I'm going to grab everything in the table and then something outside the table, like the S, and submit. I'm going to come over here in my worksheet L1. I'm going to paste it as match destination formatting. Okay, now I'm going to copy the numbers only. And then I'm going to click on this link up here, exploring quantitative data. I'm going to paste it in this worksheet called, this website called Describing and Exploring Quantitative Variables. Then I'm going to expand it out a little bit so I can see the charts. Now, theoretically, we have a uniform distribution. And typically, when things are uniformly distributed, and you take a random sample from that distribution, the histogram kind of it's not flat. Theoretically, it should be a flat line at the height, 1 divided by 24, right? But this is kind of like as good as it gets in terms of uniform distribution. We need to calculate the sample mean, and the mean is 18.39, but we need 4 decimal places. So we can't use these sample statistics because we need more decimal places. We need 4, right? So what I'm going to do is I'm going to copy them from Excel. I have to compute them in Excel first. So I'm going to do the mean, the standard deviation, the minimum, the first quartile, Q1, the second quartile, also known as the median, the third quartile, Q3, the max. At equal average, we'll calculate that. Equal STDV.S, we'll calculate the sample standard deviation, lowercase s. And then equal quartile.exe, we'll calculate the first quartile, the second quartile or median, and the third quartile. And then min and max will calculate the minimum and the maximum. All right. So here we're going to type equal average. And then I'm going to do is this. I'm going to call this time. I'm going to type time in there. We're going to get an error, right? I'm going to explain why in a second. I'm going to define a set of cells as the variable time. Now, in order to do that, I'm going to highlight A1 down to, not including the S, the last number, right, in row A65. Then I'm going to come up here to, let me widen this up. I'm going to click on create from selection. And then I'm going to make sure that only the top row is checked. What's going to happen here is these numbers are going to be named time. And notice what happens when I do that. If I highlight only the numbers, this name time shows up, right? So now when I double click on D2, equal average time, right? And time is this blue box. Okay, so that blue box is an Excel object. It's a collection of cells named time. I'm going to use that named set of cells to calculate the standard deviation, STDEV.S. Our sample standard deviation is 6.911268. Our minimum equal min, parenthesis, time. Our minimum's 8. Our first quartile, we're going to do equal quartile.exe time. And I want the first quartile. So I'm going to type 1 there, first quartile, and I get 12.25. I can also do percentile.exe time, and then I could do 25%. And I get the same thing, right? So the first quartile is the 25th percentile. Then I'm going to drag these down. I'm going to change this to the second quartile, which is 17. And I'll change this to 50%, right? So this is the 50th percentile or second quartile. And then here I'm going to change this to third quartile. And I'll change this to 75th percentile, right? The 50th percentile is the second quartile, or it's the median, right? And then all we got to do is the max, equal max time. Now I'm going to change these to 4 decimal places. Okay, so the mean of our sample is 18.3906. Our standard deviation is 6.9113. Our minimum value is 8. The first quartile is 12.25. The median is 17. The third quartile is 25. And the maximum number is 30. Now notice that our minimum in our sample is greater than or equal to 7, and our maximum is less than or equal to our theoretical maximum, right? Now I need to upload the histogram that is created by the above website. Time it takes for the next train to come. Time. Next train. I'll call it arrives. You can download as a PNG file, but I'll just screenshot it. It's histogram and downloads, right? I've uploaded that right there, and then that'll be graded manually. Okay, now let's look at the theoretical uniform distribution. So down here, this is the sample, and this is the theoretical. I'm going to call this A. I'm going to call this B. Theoretically, my A is 7. My B is 31. My expected value, theoretically, is, if I go back to this website, B plus A divided by 2. So I'm going to type equal parentheses B plus A divided by 2. That's my expected value, theoretically. And it's pretty close to the sample mean. The variance is B minus A squared divided by 12. That's the variance, right? 48. The standard deviation is the square root of the variance. So I'm going to type equal SQRT. I'm going to put a parentheses around this whole thing, right? That'll give me my standard deviation. So this is B minus A squared divided by 12, and then taking the square root of that. And I get something that's pretty close to the sample standard deviation, right? And I'll go 4 decimal places. I'm going to copy that. The median is going to be the mean because this is a symmetric distribution. 19. And it's pretty close to the sample median, right? Like the median and the mean are the midpoint of 7 and 31. The first quartile is going to be the midpoint of 7 and 19. So I'm going to type equal 19 plus 7 divided by 2, which is 13. Right? So this is the first quartile. Basically, it's the median of the lower half of the data, right? And the same thing for the third quartile. It's the midpoint between the median and the maximum theoretical value, right? So the first quartile is the midpoint of 7 and 19, 13. And the third quartile is 25. 19 is pretty close to the sample mean of 18.3906. The theoretical standard deviation, 6.9282, is pretty close to the sample standard deviation. The theoretical minimum is pretty close to the sample minimum. First quartile is pretty close to the sample first quartile. The theoretical median is pretty close to the median of the sample. The third quartile is exactly equal to the third quartile. And then the maximum theoretical value is just above the sample max. Okay, now we want to modify this Desmos.com uniform distribution with the values of A and B you were given, right? So my A and B are 7 and 31, right? Yours are going to be different. So let's click on this. I'm going to change my A to 7, right? I'm going to change my B to 31. This height is 31 minus 7 divided into 1, right? So 31 minus 7 is 24. 1 divided by 24 is that right there, right? 0.0416666667. Now I'm going to screenshot this and upload it to my math, which will be graded later. If I forget to grade your submission, make sure you send me an email to ask me to grade it. Let's do Control S, PDF. And then I'm going to click on Choose File. And there's my PDF right there, right? Now we got to answer the following questions here, part 3. These are the sampling errors of the mean and the standard deviation. So we have to calculate the difference. Take this larger value minus the smaller value. That's one way to do it. These are our sampling errors of the mean and of the standard deviation. And if there's negative number here, ignore it, right? So I'm going to copy that into here. Despite the difference between the sample statistics and their corresponding population parameters, these are population parameters that we cannot know unless we're a god. We have Greek letters, and only Greek gods know these values. Only Greek gods know this. Mere mortals can calculate the sample statistics. Despite the differences between the sample statistics and their corresponding population parameters, the distribution of the time that it takes for the next train to come appears to be uniform. Use the actual distribution to compute the following values. Now we want to find the probability that the time will be at most 30 minutes. At most 30 means 7 to 30. So what we have to do here is we have to calculate the area under this red line here that runs from 7 to 30. So the height of this distribution is that value right there, right? That's the height. And the width of this box is going to be 30 minus 7. So we got 30 minus 7, right? We're going to use some geometry principles here. This is the width of the box, and this is the height of the box. The height of the box, right? The height is 1 minus BA, right? So we're doing the theoretical. The B is 31, and the A is 7. So that's the same exact thing that Desmos has, right? And then the area is the probability, right? And that equals what? We got to multiply those together. We got to multiply the height times the width. And we get a probability equal to 0.9583. 0.9583. Find the probability that the time will be between 13 and 24, right? So this is between 7 and 30, right? We need to find 13 and 24. So we're going to do 24 minus 13, right? We're using the same height again. We're going to multiply the width times the height. The width of a box from 13 to 24 is 11. The height is 0.041667. So the area or the probability is 0.583. Now we want to find the 48th percentile, 0.48 right there. Let me pull this down here. I'm going to change this to 7 and 30. I'm going to change this to 13 and 24. Then we'll change this to the difference between these two, right? Okay, so now we got to work backwards, right? So remember, this is the product here, right? We're going to start at 7, and we want to know what this value is. We'll call this x1, and we call this x2, right? X1's the smallest theoretical value, correct? Smallest theoretical value. In this case, we want to find x2. What is this? Let me open up Notepad. Okay, so I got the probability of x less than what I'm calling x2, right? And that equals x2 minus x1, in this case, a, right? A is our minimum value, times the probability distribution. And the probability distribution is 1 divided by b minus a. And we know what this equals. It equals 0.48. Okay, so I'm going to get rid of this part. I'm going to fill in what I know. My A is 7, right? My A is 7. My B is 31, right? And now I need to know what x2 is, right? Well, multiplying this by 1 and then dividing by that, it's the same thing as just taking this and dividing by that, right? So I'm going to copy this. I'm going to multiply both sides by this value, right? I'm going to multiply both sides by that value. So that's gone. So I'm going to multiply both sides by that, right? Then I'll copy this. I'll get rid of the parentheses. And I'm going to add 7 to both sides. This x2 here is the 48th percentile. If you want to calculate a formula for this, it's the whatever percentile it is, right? 48th in this case, times the b minus a plus the a, right? And that's how you get the 48th percentile. I'm going to type equal. We want the 48th percentile, right? 48 times my b minus my a plus my a. Now let's just double check, make sure we got this. So I got equal. I'll do this. We'll take the difference of these two, right? We'll take the difference of those two, 11.5 18.52, right? This is just the height of the distribution. I'm going to multiply the height of the distribution times the width of this rectangle. And I get 0.48, right? Just double check my work. So my 48th percentile is 18.52. Find the probability that the time is less than 17 minutes, given it is at least 14 minutes. We want the probability that t is less than 17, given t is at least 14 minutes. This is a conditional probability, right? Well, let's write this as probability of A given event B. Event A is t less than 17. Event B is t greater than 14, right? And we know from the probability review in unit 1 that this equals A and B divided by the probability of B, right? Okay, so let's go back up here. We're going to write this as equal to the probability of A and B, right? So A is t less than 17 and t greater than or equal to 14 divided by the probability of t greater than or equal to 14, right? These two things are the same thing. If A is t less than 17 and B is t greater than or equal to 14, okay, so now what I'm going to do, I'm going to abbreviate the right-hand side. Okay, another way to write t less than 17 and t greater than or equal to 14 is to do this. Greater than or equal to 14, that's t greater than or equal to 14. And this is t less than 17. That right there, that statement is equivalent to saying that. Let's calculate this. So here, 14 is my x1, 17 is my x2. And then over here, 14 is my x1, and then my x2 is the maximum value that x can be, which is 31, right? Because this is continuous, t greater than equal to 14 is the same as t greater than 14. So I can get rid of the equal sign everywhere, right? To kind of make it simpler. Because it's continuous, right? All right, so now I just drag the width over. So the first width is 3, and the second width is 17. And then I just drag the height over. And I can just drag over the height times the width calculation, right? And again, I'm going to make these 4 decimal places. So the width times the height is 0.1250. The width times the height is 0.7083. I got to take this area and I got to divide it by that area to get this conditional probability. And I'll do that right here. So I'm going to take this smaller area. I'm going to divide that by that bigger area. That's the conditional probability. So find the probability that time is less than 17 minutes, given it is at least 14 minutes. That's a kind of a tricky question, right? And since we cannot know the actual distribution, we're going to approximate these numbers with the distribution from the sample. This is the theoretical, right? I'm going to copy all these numbers here. I'm going to copy all this. I'm going to paste it down here. I'm going to call this sample. We can't know the things in gray, right? So for this first thing, find the probability that the time will be at most 30 minutes, right? Same question, Same question, but we have to use a different distribution. We have to use the distribution derived from the sample. So the minimum value is not 7, it's 8. And the height of the distribution is not b minus 7 divided into 1. It's 30 minus the minimum divided into 1, right? That's the height. So this should be correct here, right? So 30 is the value I want here, right? That's the same for both problems. Now notice in my problem, 30 is the same as the maximum here. So my area is the width times the height, which is 1. So for my sample distribution, this is 1, not 0.9583. Now we got to find the probability that the time will be between 13 and 24 minutes. So these two numbers are identical, right? These two numbers are identical because they're given right here, 13 and 24. X1 is 13, X2 is 24. The width is 11. The height is, again, 1 divided by the difference in my sample maximum and my sample minimum, right? So this probability is 0.5. The width of this, rectangle, 24 minus 13 times the height, which is 0.5. Now notice that's pretty close to this 0.4583, right? The 48th percentile for the theoretical distribution, right? Remember we had B, which is 31, minus 7, right? We're going to multiply that difference by 0.48 because we're looking for the 48th percentile. Then we're going to add to that the theoretical minimum, right? So down here, we have to modify this, right? We want the 48th percentile, so that's 0.48 still. But this should be this right here should be the sample's maximum value, which is 30. This should be the sample's minimum value, which is 8. And this should be, again, the sample's minimum value, 8. Now, this right here should be what? We're using the sample, right? And this X1 is the minimum value of the sample. So it should be 8, right? So this is 8. This is, again, the 0.48 times the difference in our sample minimum and maximum, and then that product added to the minimum value, right? So our 48th percentile is 18.56, right? Now notice the width is what? 18.56 minus 8 is 10.56. This right here is the height, right? And the height was 1 divided by the difference in our sample maximum and minimum, right? And then the area, the probability between 8 and 18.56 is what? 0.48, right? We're multiplying the width of the rectangle times the height of the rectangle, and we're getting 0.48. So we just verified that in fact is our 48th percentile using sample data. Now we want to find the probability that time is less than 17 minutes, given it is at least 14 minutes. Okay, so the 14 and 17 are given by these two values, right? This 14 is given by that value, but this 31 corresponds to that 31, right? That 31 corresponds to theoretical maximum value, right? The B, right? So we have to change this to its corresponding, its counterpart from the sample. This is the maximum in the sample. Again, we can't know 31, right? We can't know 31. Now, the difference in these two values is 16. These two heights are what? All these heights are the same. So now all we got to do is calculate the area between these two values, right? The width is 3. The height is that. The probability or area is 0.1364. area under these two values, the width of that area is 16. The height is 0.0455. That probability or area is the product of those two. And then the conditional probability is this probability divided by that probability, right? And we get 0.1875. And that is really close to, that value is really close to this value. So the purpose of this first part of lesson 3 is, one, to introduce you to the uniform distribution, both theoretical and what we call empirical, right, from the sample. And then to give you an idea that we are technically making errors because we cannot know the theoretical distribution. We cannot know this up here, right? We can calculate sample statistics and get an idea of what it looks like, right? We can get an idea of what it looks like, but we can't know these values, and we don't know what it actually looks like theoretically. We can't know this, right? If for some reason we were given this information, right, then we could calculate the sampling error of both the mean and the standard deviation, right? We could calculate the probabilities associated with the actual theoretical distribution, and then we could compare them to the empirical. But in reality, all we know is this. All we can calculate are these. We can't, in reality, calculate those. We can't calculate these two numbers. We can't know what this looks like. We can't calculate these values, but we can do this, and we can compute these numbers.